For decades, billions of dollars were spent, all for Toyota to reach the number 41%, a milestone that was almost seen as the final limit of the gasoline engine. But in what felt like a blink of an eye in history, Geely responded with a number that made the old way of thinking collapse: 48.41%. With its IHEV hybrid system, Geely announced fuel consumption of only 2.22 liters per 100 kilometers, a driving range of more than 2,000 kilometers on one tank of fuel, and a Guinness World Record. So how did Geely manage to break through the wall that Toyota had spent so much effort building? Join Mandarin Tech as we explore this story in today's video. To understand why 48.41% was so shocking, imagine an internal combustion engine as a fire trapped inside a metal box. Fuel burns. The force of combustion pushes the piston downward, and that motion eventually turns the wheels. It sounds simple, but fire always produces a massive amount of heat, and most of that energy is lost through the exhaust pipe, the engine walls, and friction. That is why, for many decades, engineers at Toyota, Honda, BMW, and Volkswagen all saw the 40% mark as a wall that was extremely difficult to break through. Toyota spent years refining its technology to reach 41%, a milestone they described as almost untouchable with the dynamic force engine, thanks to the Atkinson cycle, which helps reduce wasted compression energy. But Geely looked at the problem in a different way. Instead of only trying to reduce losses, they redesigned the entire process: how air enters the cylinder, how the flame burns, how the engine keeps its heat, and how energy is delivered to the wheels. And from that point, the 41% wall began to crack. What does 41% really mean? For many decades, Toyota was the symbol of hybrid technology. From the Prius to the dynamic force engine, they proved that a gasoline engine could become more fuel efficient if it worked intelligently with an electric motor. The peak of that philosophy was 41% thermal efficiency. To reach this number, Toyota had to optimize almost the entire engine: valve timing, the combustion chamber, the compression ratio, fuel injection, and the Atkinson cycle. But after the 41% mark, everything became much more difficult. Increasing the compression ratio could cause knocking. Increasing the combustion temperature would put more pressure on the materials, and keeping too much heat inside the engine would affect the exhaust gas treatment system. That is why, when electric vehicles began to rise, many traditional car companies believed that the gasoline engine had almost reached the end of its development. And while Western car makers were busy betting their entire companies on a fully electric future, Chinese engineers asked a completely different question: what would happen if we started again from zero? That question created the first crack in the wall, and it came from a company you may already know. BYD, which stands for Build Your Dreams, looked at the traditional hybrid vehicle and basically believed that the entire design had become outdated. In a standard hybrid car, the gasoline engine and the electric motor both take part in driving the wheels. The engine constantly changes speed. It speeds up when the car climbs a hill, slows down at a red light, and shifts through a complex transmission. Every time the engine changes speed, it moves away from its most efficient operating range. From there, they asked one question: what would happen if, during most of the journey, the engine did not drive the wheels? And their answer was the DMI system. With this system, the gasoline engine mainly works as a generator, running in its optimal speed range to produce electricity, while the wheels are driven by the electric motor. As a result, the engine does not have to constantly change its revolutions per minute and rarely moves away from its highest efficiency range. The result was 46.06% thermal efficiency, the first shot proving that Toyota's 41% wall had begun to crack. While the auto industry was still trying to understand how a Chinese company could move far beyond Toyota's 41% mark, Geely was quietly preparing an even bigger leap. Their goal was to rewrite the entire way a hybrid system operates. That is why Geely did not simply fine-tune the engine in the old way. They intervened in the three most important areas: how fuel burns inside the cylinder, how the engine controls heat, and how energy is delivered to the wheels. Simply put, Geely was not just trying to make a gasoline engine more fuel efficient. They turned it into one part of a complex electrified system, where the engine, motor, battery, controller, and artificial intelligence work together to keep energy where it is most useful. The result was the IHV system, a hybrid structure in which the engine is no longer forced to work in the traditional way. It can generate electricity in a high-efficiency range, support propulsion when needed, and work with the electric motor to reduce wasted energy as much as possible. Geely's first secret begins in a very small place, the combustion chamber. In a normal engine, air and fuel are drawn into the cylinder, but they do not mix perfectly. Some areas have too much fuel, while others have too much air. When the spark plug ignites the mixture, the flame has to spread gradually from one point across the entire combustion chamber. This process happens in just a few thousandths of a second, but every moment is enough for heat to leak into the cylinder wall and turn into wasted energy. Geely solves this problem by changing the way air enters the engine. Instead of allowing the airflow to enter in the usual way, they redesign the intake path to create a high-speed swirling flow inside the cylinder, almost like a miniature tornado. When the air spins strongly, the fuel is mixed more evenly. And when the spark plug ignites the mixture, the flame no longer spreads slowly like before. Instead, it bursts outward faster and more evenly throughout the entire combustion chamber, making the combustion process sharper, cleaner, less wasteful in terms of heat, and more powerful in pushing down the piston. Simply put, Geely is not trying to burn more fuel. They are burning it in a better way. And when the energy from each combustion event is pushed down onto the piston more quickly, before it has time to disappear into the metal walls, the engine can extract more efficiency from the same drop of gasoline. But this tornado also creates a new problem. When combustion becomes faster, the pressure and temperature inside the cylinder also rise higher. That makes the engine more likely to suffer from knocking, a destructive phenomenon that can damage the piston if it is not controlled. The hotter and more heavily compressed the combustion process becomes, the higher the risk of knocking. This happens when the fuel ignites by itself before the spark plug fires, creating an uncontrolled explosion that can crack the piston and destroy the engine in just a few minutes. This is also the reason Toyota stopped at 41%. They did not dare to push compression any further. To solve this problem, Geely chose to divide the engine into two different temperature zones. The cylinder head, where combustion takes place, is cooled more aggressively to reduce the risk of knocking. When the upper section is cool enough, the air-fuel mixture becomes more stable, allowing the engine to withstand higher pressure without destroying itself. In contrast, the lower engine block, where the piston constantly slides up and down, is kept warmer. The reason is very simple. When engine oil is warm, it becomes thinner, helping the piston and other moving parts slide more smoothly, thereby reducing friction. In other words, Geely created an engine with two states at the same time: cool at the top to control combustion, and warm at the bottom to reduce mechanical resistance. This entire process is controlled by an electronic cooling system, which can adjust the flow of coolant according to real operating conditions. As a result, the engine can burn more powerfully, handle higher compression, and reduce internal friction at the same time. This is not a small upgrade. It is a revolution in the way engineers think about thermodynamics. And thanks to this bold separation, Geely pierced through the second wall that the entire industry had once surrendered to. After controlling combustion and temperature, Geely still had one major problem left: how to deliver energy to the wheels without losing it through the transmission. In traditional cars, energy from the engine has to pass through many gears, clutches, torque converters, and drive shafts. Every component creates friction, causing part of the power to be lost before it reaches the wheels. Geely chose a different path. With the 11-in-1 EDHT system, the gasoline engine no longer has to pull the wheels most of the time. It mainly runs in its high-efficiency range to generate electricity, while the electric motor directly drives the wheels. Only when the car is cruising steadily at high speed, above roughly 130 kilometers per hour, Does the system connect the engine to the wheels if that method is more efficient? In other words, IHEV does not completely eliminate mechanical drive. It only uses mechanical drive at the right time and in the right place. However, for this system to operate smoothly, Geely needs a brain fast enough to decide when to use gasoline, when to use electricity, when to combine both, and when to lock the system directly. That brain is the Artificial Intelligence Energy Management System. This artificial intelligence works continuously, reading dozens of parameters every second: vehicle speed, the slope ahead, battery condition, engine temperature, and even positioning data. It calculates 50 times per second to choose the optimal path for the flow of energy. For example, when you are driving uphill, the artificial intelligence can use electricity from the battery to assist the car, reducing the load on the gasoline engine. When the car goes downhill, it activates regenerative braking to recharge the battery. Everything happens automatically, without the driver needing to do anything. After everything Geely has done inside the IHEV system, the most important question remains: what results does it actually produce in the real world? The combined result of all these technologies, the tornado-like combustion system, the separated temperature zones, the 11-in-1 electric drive unit, and artificial intelligence power routing, is a certified fuel consumption figure of 2.22 liters per 100 kilometers. That is a Guinness World Record for a mass-produced vehicle. With a full tank of fuel, the car can travel more than 2,000 kilometers. To put it simply, this level of fuel consumption is equal to about 45 kilometers on just 1 liter of gasoline. An extremely impressive number even for a small car, let alone a hybrid system designed for mass-market commercial vehicles. What makes IHEV especially notable is that it is not only fuel-efficient on paper. The vehicle uses the electric motor to deliver smooth power in most everyday driving situations, while the gasoline engine only operates when it is truly needed and when it can reach its highest efficiency. With a two-motor P1 and P3 structure, an integrated 11-in-1 electric drive unit, and a drive motor with power output of up to 230 kilowatts, IHEV can respond quickly at low speeds, especially in urban driving. Therefore, the result of IHEV is not just a car that uses less fuel. It is a new hybrid model, smooth like an electric vehicle in the city, convenient like a gasoline car on long journeys, but with fuel consumption so low that it forces the entire industry to ask a new question. A thermal efficiency of 48.41% does more than break a technical record. It also challenges the belief that the internal combustion engine has reached the end of the road. Geely's IHEV shows that the gasoline engine may not be dead if it is placed inside an intelligent system where the engine, electric motor, battery, and software work closely together. For users, the benefit is clear: smooth like an electric vehicle in the city, but still convenient like a gasoline car on long journeys. The electric motor delivers smooth and responsive driving in urban areas, while the gasoline engine still allows quick refueling in places where charging infrastructure remains limited, such as Southeast Asia, the Middle East, South America, and rural regions. For Japanese and Western car makers, this is a major challenge. Toyota once dominated hybrid technology, while Europe once led the world in internal combustion engine development. But now, the thermal efficiency record belongs to a Chinese company. This shows that China is no longer competing only through electric vehicles, batteries, or lower prices. It is also moving deeper into core technologies such as thermal management, electrified powertrains, artificial intelligence, and energy control. Geely is not simply improving an old hybrid model. It is redesigning the entire way the vehicle operates, allowing artificial intelligence to continuously decide when to use gasoline, when to use electricity, when to recharge the battery, and when to deliver power directly to the wheels. Therefore, IHEV is not only a fuel-saving technology. It could become a practical bridge in the transition from gasoline vehicles to electric vehicles, using less gasoline, using more electricity, and allowing software to optimize every flow of energy. 48.41% proves that Toyota's 41% wall is no longer impossible to break. Geely achieved this through faster combustion, 2 temperature zones, an 11-in-1 electric drive unit, and artificial intelligence energy management. The result is 2.22 liters per 100 kilometers, more than 2,000 kilometers on one tank, and a Guinness World Record. Geely may not have ended the gasoline engine, but it has opened a new chapter. Is IHV the smartest bridge to electric vehicles, or the final breakthrough of the combustion engine? Share your opinion and subscribe to Mandarin Tech.